Good day, ladies and gentlemen, and welcome to another edition of Prometheus University. In today's edition, we will be discussing the basics of shear stresses in beams. The basics of shear stresses in beams. And as usual, we would try to develop an intuition of the stress based on the deformation that it introduces on the member. And then we go ahead to give a geometric and algebraic representation of this intuition and identify particular parameters that are unique or that are particularly helpful in helping us calculate, helping us evaluate, helping us understand and predict and design for the particular stress in question, in this case being shear stresses. So let's start with the intuition piece. Now consider we have two plates here, two blue plates seen here in 3D view stacked on top of each other, and we pin these together with this red pin. It could be a bolt. And now let's take a section view of the plate at the point where the pin is. Draw that below there like that, and we apply a force to either plate, one going to the left and one going to the right, and we pull on this to the point where we deform and fail the pin, the red pin, in the manner shown here. Now the question is, we all have an intuition for this. We've all seen this before. We call this shearing. We say we have sheared the bolt. Now we have these different names associated with different deformations introduced to members by different kinds of stresses. Now we look at this and we say, well, this is not tension because we did not pull it apart, right? This is not compression. We didn't push it together and buckle it and so on and so forth. This is not bending. We didn't bend it and therefore introduce tension and compression to the cross section. We didn't do either of that. This is a different kind of deformation, a different kind of failure, and we call this shearing. And this is the action of pruning shears or scissors. These things shear things apart. Now I should mention right now that in order to go deeper into this and understand the mathematical representations that we're about to indulge in, a knowledge of bending stress is assumed. So watch the first two parts of our bending stress series, Basics of Bending Stress Analysis and Design, part 1 and 2, where we come up with the section modulus and the MC over I equation and the moment of inertia. Those two videos and their contents will be quite helpful in understanding the mathematical representations of our intuition in this video. And some other pieces of information that are implied here are a knowledge of static equilibrium, right? Basic knowledge of static equilibrium, and shear and moment diagrams in beams. Let's go ahead and make a statement about what we just intuited. Let's go ahead and state that shear stresses involved the sliding of one plane against another, and we can intuit that what we just did with that bolt involved the sliding of the top plane against the bottom plane at that point of intersection of the two plates. We sheared the bolt by the sliding of these planes relative to each other, and that's what shearing essentially is. Now, how do shearing stresses get introduced to a beam that is primarily in bending, a member with length that's transversely loaded and that bends? How do the shear stresses get involved? Well, let's consider that. Let's look at a diagram here, and the top shows a beam which is made up of 3 layers. Maybe it's 3 pieces of plywood. Maybe it's 3 rulers just stacked up against each other. And the top part is unloaded. The bottom part is loaded with loads transverse to the length of the beam, shown with arrows pointing down. And then we have a deformation, our usual smiley face deformation. Now, what is particularly apparent, especially on the ends of the beam, is that these 3 layers that make up the beam have slid relative to each other. So at the plane that forms the point of intersection, the two planes on the top and the bottom, let's say, that form the points of intersection between these, there's been relative sliding. This is how the shear stresses get introduced. In a beam with where the planes are integral, made up of a continuous homogeneous material, the stresses that keep the layers together are the shear stresses. So if we consider a piece of the unloaded beam, we see a rectangular portion, unloaded, unstressed, undeformed, and we consider a portion of the loaded beam, we have on the top and on the bottom these shear stresses that keep the pieces together. Now, we notice that this representation here of a force on the top and the bottom form a force couple that cause a clockwise rotation of this. Static equilibrium does not allow that. We're going to need to have another set of forces on the sides that cause a counterclockwise rotation that keep this system in static equilibrium. So we have seen how the sliding of one plane against another is introduced in beams. We have looked at the geometry of the deformation and the forces or the stresses involved with some intuition guided by the concept of static equilibrium. So let's take it a step further and notice that the forces there going to the right and up, the shear stress to the right and up, can be resolved into a single vector, right, going to the right and the top. And similarly for the force going down and to the left. So now what does this look like? This is essentially what's going on. And what we're doing is we seem to be pulling apart this piece. We're pulling the piece apart such that if we continued, we would fail in tension along this line here, this jagged line I've drawn in a kind of a 45-degree orientation. Hence, in brittle materials that don't have a lot of elasticity or will not continue to ductily deform in the plastic region, but that will brittly fail in tension. In such materials, we can clearly observe, an example being concrete, we can clearly observe this 45-degree failure mode, or failure plane, I should say, in the shear failure mode, right? Now, some of this would be already familiar to those of you who are studying mechanics of materials or design of concrete and so on and so forth. You have seen this idea of the shear failure plane occurring at 45 degrees. You are familiar with the geometry of the deformation and the forces that we've drawn. And we've also just seen how the sliding of one plane against each another is introduced in a beam. So now let's take it a step further. Just like we did in our bending stress series, let's look at the formula for shear stresses, and then we will work backwards from the formula using our intuition so far, guided with our concept or guided by our concepts, to derive the formula and see if it all makes sense to us. So it states here that shear stress is equal to VQ divided by IB. Okay, well, what does V mean? What does Q mean? And so on and so forth. Well, let's define those terms. V is the shear force at the location where the stress is to be determined. The moment of inertia is what I is. We know that concept. We might wonder what it's doing here and why it's related to this. That we will see, hopefully. The width of the beam, the width of the cross-section of the beam at the location where the shear stress is to be determined is the B parameter. And then we have this Q parameter. And it's called the first moment of outer area. It's really the first moment of area relative to the neutral axis. And we'll see what that is doing in there as well. That is really the new parameter that'll fall out of our description, our mathematical description of this shearing intuition which we're trying to develop. So here we are, and our task is to stumble upon, or as they say, derive this equation by expressing in mathematical terms our intuitions so far from shear stresses and bending stresses and what have you. So let's get right to it. Let's go back to our beam. We have a beam here, simply supported. We label the x direction as x, the y direction as y. It is loaded with a distributed load, a load per length called Wx, right? We define that load as Wx, and we take a little piece of this beam, a little piece of the length of the beam, dx. So we're not looking at the cross section, we're looking at a piece of length along the x direction, okay? So we have dx, we have Wx on top, we draw the parallel, we draw a line through the neutral axis, that's the green line. The depth of the beam is d, the distance from the neutral axis to the outer fiber is c. So far, so good. We're used to seeing this kind of diagram. Now let's draw the forces in here to balance out that Wx. There's going to be a shear force, V. We draw that to the left, and then it's going to be in the opposite direction, V plus dV, another shear force to the right. Now, dV exists because we have Wx, a force per length, and we also have a length, dx. So dV is basically the integral of Wx dx. dV is there because we have a force per unit length, and we also have a length between the left side and the right side. Therefore, there will be an additional shear stress, dV. So what else do we have in this beam? We have moments, don't we? We have a moment m to the left, and we have a moment m plus dm to the right. Now dm is there because we have a shear stress v, a shear, shall I say, v, and we have dx. We have a shear and a distance through which the shear travels, if you will. That creates a moment. And we know this from our study of moment and shear diagrams. A knowledge which I stated in the beginning was assumed in this video. So now we're going to state that fact here, v dx is equal to dm, right? And we're going to put it in a box and call it equation 1 because that equation is going to come in handy in a second. Now let's show what the bending stresses look like, right? What are these forces in the horizontal direction? What do they look like? Oh, we are familiar with this, the tension and compression couple basically, and watch our first two parts of the bending stress series to familiarize yourself with this. So we have to the left sigma 1 and to the right sigma 2. Now sigma 2 is greater than sigma 1 in this particular case. Let's say it could be reverse, sigma 1 could be greater than sigma 2, but we have a scenario where the moment is changing across the beam, right? Because it's loaded transversely, the moment will be changing across the beam. We know this from, again, our shear and moment diagrams. And hence sigma 1 and sigma 2 are not equal. In this case, we're going to consider sigma 2 to be greater than sigma 1. Now sigma 1 and sigma 2 can be determined simply with the equation my over I, and this is something that we elaborated on rather deeply in our first two videos in the bending stress series. So let's remind ourselves of what we're doing. We're talking about the sliding of horizontal planes against each other and the stresses involved with that. So let's pick a horizontal plane. Let's pick a horizontal plane here represented by the black line, which is a distance y below the neutral axis. Okay? The distance y below the neutral axis, we have a black line which represents a plane, and we're going to go ahead and find the shear stresses in there, armed with the facts and intuition which we've developed so far. So let's take this 2D view into a 3D view. So that black line now is represented by a black plane shown below. We have the length dx, but now we're also representing the width of the beam b. We have the depth of this block, if you will, is c minus y. C is the distance from the neutral axis, of course, down to the extreme fibers, and y is the distance from the neutral axis to the plane we're concerned with. Hence, the depth here is c minus y. Now, we can say something about the horizontal forces here, which is what we're concerned with. We already know that the horizontal forces, we know of the horizontal forces that are generated by the bending stresses. So let's go ahead and place those there. Gamma 1 to the left, gamma 2 to the right. And since we know, we've already stated, that gamma 2 is greater than gamma 1, we're going to have a shear stress represented by tau here, but represented by the arrow, the red arrow going left, that's going to be going away from gamma 2. Okay, so all we've done here is we've selected the plane to consider. The plane is a distance of y below the neutral axis, right? Which will turn out to be the same if we chose the same distance y above the neutral axis. But what we do next is we show the forces in the horizontal direction. We have gamma 1, we have gamma 2. Gamma 2 is greater than gamma 1. We have a resultant, or for static equilibrium, we have a force, a stress, tau, going away from gamma 1, and that's what we've shown. We can state something about this scenario. We can write an equation of static equilibrium that sums up the forces. So basically what we're going to say is that shear stress multiplied by the area of that black plane, which is basically b times dx, right? We say that tau b dx is equal to gamma 2 times dA, and dA is basically the distance c minus y times b, right? So we represent that as dA, minus the integral from c to y of gamma 1 dA, right? So all we've done here is a statement of static equilibrium. We're saying that the force going to the left equal the forces going to the right, right? So therefore, the stress times the area of the black plane, the shear stress times the area of the black plane, is equal to gamma 2 dA minus gamma 1 dA, the integral from c to y of gamma 2 dA minus the integral from c to y of gamma 1 dA. Okay? Now, we know how gamma 2 and gamma 1 are defined. We've seen that in our equation number 2, right? Excellent. So now we just have to replace gamma 2 and gamma 1 with the expression, right? The expression that expresses them in terms of their moment and cross-sectional properties. So we rewrite the equation as such. We say that tau b dx is equal to the integral of c to y of m plus dm y over I, right? Because sigma 2, again, is m plus dm y over I dA, minus the integral from c to y of my over I dA. Okay, because sigma 1 is my over I. Okay, so we've simply represented, or replaced, I should say, the formula for the bending stresses into our equilibrium equation that sums up the forces in the horizontal direction for the plane that we're concerned with, right? Okay, so moving forward, we can rewrite this equation as follows. Okay, we can separate the m and the dm, right? Such that now we have this equation that's tau b dx is equals to m over I y dA plus dm over I y dA minus m over I y dA. Okay, and what we've basically done is we've separated out the terms, and we've put, as is done with integrals, the constants over to the left. So now we notice that we have both on the right side a positive value m over I and then the integral of y dA, and we have a negative value m over I integral of y dA. So those two cancel out, right? So far, simple mathematical operations going on. Okay, so now we cancel those out, and then we rewrite our equations as tau b dx, again, the shear stress multiplied by the area of that black plane, is equal to dm over I, again, these constants out here, multiplied by the integral from c to y of y dA. And here we are. Okay, we can rewrite based on equation 1. Notice that equation 1, which we've stored there, says the integral of v dx is equals to dm, which also implies that dm dx is equal to v, which is the shear. So dm dx is the shear stress, the shear force, which is basically saying the slope of the moment diagram is equal to the shear, which is something that we know from shear and moment diagrams. Now, if we go back to our equation, we can rewrite this as tau is equals to dm divided by b dx over I, right? And then multiplied by the integral of y dA. And we just noticed that dm dx is equal to the shear. So we take that out and we write it as v. So now we have tau is equal to v over b over I multiplied by the integral from c to y of y dA. Now the integral of y dA is one of those cross-sectional properties that we can isolate, right? It is not a constant, it's changing, just like the moment of inertia and so on and so forth. And we can take it and we can say, hey, what is this value? Well, this value is what we define as the first moment of outer area. It is the first moment of area taken from the neutral axis. Just like the moment of inertia is the second moment of area taken from the neutral axis, by the way. But this we rewrite as Q. This is the mathematical object that has fallen out of this is the useful mathematical object, the one that is particularly helpful in helping us to find the shear stress. It has fallen out of our expressions of our intuition, right? Our mathematical expressions of our intuition, just the way similar to the way in which we came up with the section modulus and the moment of inertia. So we replace this integral of y dA with Q, and voila, we have that the shear stress is equal to VQ divided by IB. And again, where V is the shear force at the location where the stress is to be determined, I is the moment of inertia of the beam cross-section, B is the width of the beam cross-section, and Q is the first moment of outer area. We can manipulate this, so we can study this equation, apply it to different cross-sections, and we will notice that there is a parabolic distribution of shear stresses, right, where the maximum shear stress is located at the neutral axis, directly opposite to the moment or the bending stress, which is A, linear, and secondly 0 at the neutral axis. Okay, the shear stresses, on the other hand, have a parabolic distribution and are 0 at the outer edges and maximum at the neutral axis. So again, what have we done? We have looked at the concept of shearing, came up with a direct intuition of shearing a bolt or using shearing scissors. We looked at how this involves the sliding of one plane against another. We looked at how this sliding is introduced, came up with some kind of a way of visualizing how this sliding is introduced in beams. And then, using our knowledge of bending stresses, static equilibrium, shear moment diagrams, we came up with the formula for finding shear stresses at any plane along the cross section, and that is the formula VQ over IB. Thank you very much, ladies and gentlemen, for watching another episode, another edition of Prometheus University. If you enjoyed this, please share, please spread the word, please leave a comment, and also subscribe to our page. Thank you very much.